So you may remember last year that we did a system where we went from XY coordinates to radius angle coordinates. And this is done in a couple of methods, in a couple of ways. One of them is that whenever you do functions in polar coordinates, it's almost always set equal to radius, and it's r of theta. Whereas when you do them in terms of rectangular, it's almost always set equal to y. I didn't like that because if you look at the notation, it's a little bit backwards in terms of r and theta. But I'm going to have to succumb to the fact that every book I've seen does points in terms of r theta. It'll probably change it for next year in pre-calc because I always did coordinates in theta comma r. So for you guys now, we're going to go r theta to be consistent with the book, and just keep it in that order. So your coordinates for polar coordinates are going to be in terms of radius comma angle. Now, the conversion between them is super easy when you're going one way and not as bad when you're going the other way. So if I want to go from polar to rectangular, and I want to convert I don't know, let's do 3 comma, or negative 3, 4. So that's not polar rectangular, that's rectangular polar. Save that one. Let's just do a radius of 3 and 3 pi over 4. Okay. Nowadays, you can either graph that and kind of see what the relationship is. I tend to be a very visual person and like the graphs. The first couple of problems want you to graph, and they want you to see what quadrant that's going to be in so you can get your sign straight. But the mathematical way is just x is equal to, do you remember this?
Sine, cosine, tangent.
Remember, this is r and this is theta.
Yeah.
So it needs to have both of those in. R
Cosine
theta, and y is r sine theta. So if I was taking this and converting it to rectangular, I would do, hang on, I'm going to quickly start the calculator program because I want it in about 5 minutes. So I would get an ordered pair of 3 cosine 3 pi over 4, 3 sine of 3 pi over 4. Since I have the graph here, I might as well graph it using the big one I've got here. It's I kind of almost always label these, and then I label the sides here so I know where the 45s are and I don't have to hunt for them all the time. But 3 pi over 4 is a 45-degree angle in quadrant 2. If I keep them exactly where they are, it would be right here. Obviously, rescaling it would move it out much greater. This is a pretty substantial number of radii you have on this polar graph. But its rectangular location would be 3 times. The cosine of that is negative 1 over root 2. And the sine of it is 1 over root 2. And obviously we're fine now leaving it as 3 over root 2. Negative 3 over root 2, 3 over root 2. So that's polar to rectangular. It is by far the easier of the two.
Did you just pick a random circle?
No, that's actually 3 out. It's 3 out from the middle. Okay, rectangular to polar. Let's go with a pen that is not all fuzzy and colory. We're going to go
Ooh, there you go.
negative 3, negative 4, and I want to take that to polar. Okay, that is open.
Don't you just do
So the angle, yes you do. The angle you get from the arctangent, and you have to pay attention to angle. So the angle is equal to the arctangent of negative 4 over negative 3. But it's kind of a pay attention to quadrant. So your book is going to ask you to do between 0 and 2 pi for the angles. Arctangent only outputs negative pi over 2 to pi over 2. So especially with the negative angles, you're going to have to kind of interpret where that is. This is going to output specifically, and I'm going to do this in a sense where I leave this leave this in its exact values. So the arctangent of 4/3 in quadrant 3, which is where I want this to be, is actually what angle? How would I leave that as an exact value, knowing that arctangent of 4/3 is the exact? So I'm asking is, what's the angle left is an exact value, a value you can plug in your calculator and you can get it. I want it quadrant 3. Arctangent of 4/3 is going to output a positive angle, but in quadrant 1.
So 180 minus.
Not 180 minus, that'd be quadrant 2.
Can you just subtract pi from that?
Okay, subtract, plus would be it.
Why would you?
It's going to give me this angle right here. I want this angle right
Oh,
here.
you just multiply
Add 180.
Add 180, but we're in radians, guys.
Pi.
Add pi.
My angle is pi plus arctangent of 4/3.
Didn't you say it was negative pi over 2? That's where it outputs it, so you have to make sure it goes.
Yeah, that's what. Thank you. I just meant arctangent outputs those kind of angles.
Oh.
This specific example is going to output a positive number.
No,
I want quadrant 3. So I am okay. Your book is probably, I haven't checked its answer key yet, but it's probably going to give you an approximation as well. I'm okay with you doing this without approximations because I know you know how to type this in your calculator. What's the radius?
5.
Yeah. This is not the best example to use because it's an easy one, but that's how you get angle. To get radius, you just use r squared is equal to x squared plus y squared and do a Pythagorean on it.
What is that?
This is a triple, so my r comma theta is going to be equal to 5 comma pi plus arctangent of 4/3.
Could you do?
You could. So a second position for this, and there's a section in your book that asks you for a second ordered pair that's the same position, but is also within the same 0 to 2 pi.
Negative and.
So we make this a negative angle
And just take away the. Oh, and then
and take away the pi, and it's just arctangent
That's good.
of 4/3. So in one case, I'm actually going pi plus and doing the positive angle. In the other case, I'm saying, here's the angle right here, but I'm going to go negative with my radius and pop over into the other quadrant. So there is a section in your book that asks you to do 2 points, both within 0 to 2 pi, that are the same position. A lot of times we get like infinite number of points. This can only be 2 possible things. Yes, Colton?
Do you always have to do pi plus the arctangent? Is it always that? Like that?
It's not always that. My specific ordered pair right here was in quadrant 3.
Okay.
So since arctangent outputs an angle in quadrant 1, to get the specific position in quadrant 3, I had to do that angle I got plus pi.
If it was like in quadrant 2, so you plus
Pi minus. Well, if it was in quadrant 2, first of all, arctangent would have outputted a negative angle. So it would have just still been pi plus because it's going to be a negative value. I don't like saying always. I like just thinking about where is my positioning.
And if it's in 1 or 4, you don't have to worry about.
Yeah, well, 4 you would because your question asks for 0 to 2 pi. So in quadrant 4, arctangent's going to output a negative value.
Does it add 2?
So you're going to add 2 pi, yeah. Now, calculator, this is something I do want to teach you. And this is going to be a review for some, but not for others. Your calculator has a very interesting way of doing this conversion. And this is going to be useful for where you want to go rectangular to polar or polar to rectangular. So let's practice this with the calculator. I'm going to give you rectangular coordinates of 2.1 comma 3.5, and I want to take that to polar, and I want to do it in a single step. And I'm doing this in a single step because if I do this right, then I don't ever have to truly think about it. I can just like go really quickly. And if this is a multiple choice problem with calculator on an AP exam, we can go quickly. The trick here is to rely on something we know. I need to take this ordered pair and express it as a single number. Not an ordered pair of numbers, one number. But I can do it in complex numbers. What is 2.1 comma 3.5 expressed as a single complex number?
Something with eyes.
It is something with eyes.
The eyes have it.
You're making this more complicated. 2.1 plus 3.5 I.
That's right. That's the rule. That's the
Because in our complex number system, this was the real numbers, this was the imaginary numbers. And so 2.1 plus 3.5 I meant right 2.1 up 3.5. Okay. Now, in your calculator, and let me shrink this down.
Are we using a TI Inspire or TI 84?
Yeah, this is Inspire. I'm going to write 2.1 plus 3.5 I. And then I'm going to go Menu, Number, Complex Number Tools, and I'm going to convert to polar. Okay. Now, we're going to interpret this in a second. This is not as bad as it looks. Your output, I'm going to come right back over here. When I have a plus bi, that is equal to radius times e to the theta I. All you're looking for is what's the radius and what's the theta. So moving back over here, your radius, it's going to put after, I don't know why, I mean your calculator just does that so you can see the thing. But what's your radius here? 4.08, and your angle is 1.03, and that is in radians. So we can say that 4.08, 1.03, via calculator, that is actually equal to radius of 4.08, theta of 1.03, and I can put that as an ordered pair, 4.08, comma 1.03, which is an r comma theta. This is the key right here, though, putting numbers into this format so they appear as a single number. Both of them are complex numbers. This complex number is the rectangular version. This complex number is the polar version. So if I want to go the other way,
Just do the same thing. Convert.
we're going to go polar of, let's say I have a radius of 7 and an angle of negative 2.18. And that's 2.18 radians. So you can add your 2 pi if you want, but you don't have to for this. What I'm going to do is plug that in as 7e to the negative 2.18 I. I drove myself crazy this morning making some of these notes, and I was forgetting to put the I in, and I was converting it to rectangular. And if I don't have the I in, the rectangular is just really that number. So just be careful with the I. So I'm going to type that in. 7 times e to the negative 2.18. And go to the pi button, hit the I. Now I'm going to go right and like move the cursor right so it kind of expands. It's bigger. It's kind of away from that. Now I'm going to go menu. Kidding. Come back. Menu. Number.
2, 9.
Step to convert to rectangular. And it's going to give you an a plus bi number. Negative 4.0, negative 5.7.
Flip.
I'm going to go one more just to be consistent. Okay, so that's using a calculator to convert. It's, again, a useful thing. You know how to do that. I was looking all to see if there's like an easier way to do it, and that became the easiest way. It's just nothing that's explicitly stated in your book. Your book does have this section where it says, like, using the angle feature of the graphing utility. I'm actually going to eliminate the thing. I do want you to do 7 and 9. It takes 2 seconds, but it's useful practicing that so that you can do it quickly if you've ever seen it again.
2 seconds each or 2 seconds combined?
Probably each.
That's 4 seconds.
Okay. Last major section, and that's sketching graphs.
He's just spoofing this. Oh, you bet your ass I am.
Let me pause this for just... We do. Resuming. Graphing. Some graphs are easier to graph in their polar form. Some graphs are easier to graph in their rectangular form. It's just kind of a thing. So to start, if I just give you a graph of like radius is equal to 3, that's kind of a 50-50, but I'd say it's slightly easier to graph in its polar form. If radius is equal to 3, angle is whatever. So that is a graph of a circle of radius 3. Just likewise, if I get a graph of theta is equal to pi over 4, you can convert that into rectangular coordinates. You don't have to. If you graph that on an xy grid, y, Why did you do that to me? I don't want a new page. I want my cursor down here. Give me a full view. Hang on, it is deciding to disconnect, and that's why it's freaking out.
What's the R? Then it's just a line.
R could be anything.
So it's just
the R could be anything.
it's just a line.
It's just a line. Okay, I'm coming back here. Okay, so if I have a graph of that, and theta is pi over 4, so it's a 45-degree angle. In my early days, I used to teach that was a ray before we actually realized that radii can be negative. So this is just positive radius, negative radius. That is a theta of pi over 4. It's just a line. And if you do the conversion, realize theta is equal to pi over 4, you can kind of go tangent of theta is equal to the tangent of pi over 4. Tangent of theta is y over x. Tangent of pi over 4 is 1. You just get y is equal to x. So you can convert back and forth between them. And applying tangent to both sides can be a way to do this as well. Okay, for number 3, let's do r is equal to secant of theta. Anytime you're converting polar into rectangular, you're using every bit that you have to try to get this back into x's and y's only. So secant is just defined as 1 over cosine, which is r over x is what I was going for. And if you multiply both sides by x, you get x is equal to, divide both sides by r, which you can do because r is usually not 0, 1. This is just the line of x is equal to 1. I did not need it to do that. Okay, there's that. X equals 1. Okay, moving on. Graphing, yes, I'm recording. Graphing in polar coordinates is easy in your calculator. I mean, I'm just going to show it. You can go to, you can open up graph. Okay, fine. But the thing is, if you have a graphing system that doesn't have polar but does have parametric, which is common on a lot of computer graphing systems, one thing you can do is for parametric equations, you can say x of t is equal to the function of, in terms of theta times the cosine of theta, and y of t, sorry, not y of t, this is y of theta, is equal to the function times the sine of theta. So, and I'm going to kind of erase the f of theta and just put an r of theta, because that's how I've been sort of calling it. This is a way to graph it in parametric, if you would need that. We're not going to do that much, but I just want you to kind of have that little trick on hand. We can typically graph in parametric, or graph in polar on our graphing calculators, so there's not really a whole need to. Okay, another graph, a little more complicated one, is to say r is equal to 2 cosine 3 theta. And some things to know about this that we never truly described. Last year we just kind of let you guys sort of figure it out. But I know that my max value of, I would say my max radius is 2. So if I'm trying to, I'm going to grab one of this grid down and pull it and copy it down. So copy and put that here. Okay. I know that essentially what's happening is that as my angle increases, my radius is cycling between 2 to 0 to negative 2 to 0 to 2 to 0. You're going to get a shape that starts to look like this. And you don't know quite how that's going to play out just yet, but it starts to cycle back in sort of a circular method. Now, I'm not too concerned with doing the mass amounts of t-charting here, but we can do a few points. I know that as theta is 0, let's do theta cosine 3 theta, and then 2 cosine 3 theta. When theta is 0, cosine of 3 theta is 1, which makes this 2. So my starting point is 2. Now I'm going to expand my grid out so that I've got 1. I'm going to call this 2 right here, put a point. That way I can get this, this, this. You guys have a much better grid than I do, but or much tighter grid. Okay, now as I increase theta, essentially what I want to do is make, I'm going to add another column before this, like add a theta column. I want to make 3 theta be something that I know. Like I know theta over 3. And the cosine of theta over 3 is 1/2. And 2 times the cosine of 1/2. But that comes from an actual theta value of theta over 9. Which is not something that you can typically easily graph on this grid. I know that theta over 2, the cosine of theta over 2 is 1 over root 2, which is root 2 over 2. And the only reason I'm writing it as root 2 over 2 is because then 2 times that is root 2, which is about 1.4. And my original theta right here would be divided by 3, theta over 6. Theta over 6 is this value right here.
Pi over 6.
Or pi over 6, sorry. And that is 1.4, so it's going to be about here-ish. So I'm going to get something that connects like that. And
Did you get your 1.4? Did you just eye it?
yeah, I eyeballed it. This is pi over 4. When I get pi over 4 here, 3 pi over 4 is my 3 theta. Cosine of 3 pi over 4 is negative root 2 over 2, which would be negative root 2, or negative 1.4. So when I'm right here at pi over 4, I'm already at negative 1.4, which, let's follow this around, put a point here, put one here, and put one there. So negative would be somewhere in there.
Cosine of pi over 2 is 0, dude.
Oh, that is. Why did I mess that up? That's 0. That's 0. So this is 0. And this is negative. So I'm actually tighter. This is going to come out like that. And swing out like this. Anyway, I'm going to sort of draw like a little sketch of what this is eventually going to look like.
Just go roll around.
And I'm not so concerned that you guys can graph a ton of these by hand. But I do want you guys to like remember a little bit about what these are like. This type of graph has a specific name. They call it a rose curve.
Why? It looks like a rose.
It looks more like a tulip, but
Or as you add stuff,
Yeah, I don't think it looks more like not a rose, but like a flower.
looks a bit like a fidget spinner.
Rose curves come
Yeah,
from
but-
r is equal to a times the cosine of n theta, or r is equal to a
Signing.
times the sine of n theta. And you have typically n petals when n is odd, and you have 2 n petals
For this even.
when n is even. And we obviously have a much better way to look at what's happening with this than to continue to graph this completely by hand, which if you know me, you know what we're about to switch to.
The calculator.
No. A calculator.
Decimals.
Yep. So let's get a few visuals down of what these look like and how changing your n value changes the number of petals
We're
and
gonna
makes
get
it
some
look.
sliders.
We are.
Yes. The best part.
Well, we actually did this last year. Like I showed you what this looks like.
I remember.
You know what we didn't do last year? A calculator art chapter. You have any idea how badly I want
Do you know why we didn't?
Because
We had one more week in the second semester and one less week in the first semester last year.
Duh.
I'm so glad we didn't do that, dude. It would have been doing it like 10 minutes before this, dude.
R equals, and I wish we had,
That
a
would've been fun.
It would not have been.
cosine
I don't know, listen, man.
of n
I would not have wanted a math project. Just the word.
theta. Let's minimize that. Let's turn on projector mode and take a look. Okay, so A, we're just going to keep, let's make A bigger so we can see it. And you can actually go into the graph settings and change the grid into a polar grid so you can see it a little bit better. And as I slide N, nope, stop it.
Wait, what? I thought it was.
Because it's really hard to get N values that are even. But like there's 3, there's 4. When N is even, you have double the number of petals.
What about when it's not an
When N is 5, you got that. When N is not an integer, like what's happening with this graph is that at a certain point it starts to come back on itself. But when it's not an integer, it slightly shifts off a little bit. So if I see 5.1, it's like that slight shift means this is still almost like a 5-petal thing, but like what you're seeing is 10 minor ones happen before it comes back on itself. So like if it's 5.2, you should see like 5 minor ones happen, but those start to be evenly spaced. 4, 5.
Looks like a slinky.
So you can kind of play around with that all you want. And then sine doesn't do anything other than just slightly rotate it. So that instead of being where it is now, it's just like shifted just a little bit. And then you know what A is going to do.
Make it bigger or small.
Yeah. Okay. That's one general type of curve. Let me give you 2 others. Okay. That was the rose petal. I have never, ever, ever really learned correctly how to pronounce this, or even how,
We're gonna have a field day with this.
or even how to draw this freaking C with a little squiggly under, the one that's swan.
Well, I know it's in, like in Barcelona, I think. Alabica?
Somebody look up how to say this damn word.
Lemniscates.
Limassol.
Curves.
It's limassol.
I'll figure it out.
This occurs when you take what would be a rose petal and you're adding a constant to it, or subtracting a constant to it, or subtracting it from a constant. Like that's where this happens.
You
So
still need N or no?
you can have an N. I'm just going to leave it off for now. N's going to make it a lot more complicated. So we call these cardioids because sometimes they look like this. Limassol.
Yep.
Thank you.
You're welcome.
You shouldn't have told us the correct way. And
Hang
that
on.
will never say.
Limicon.
Limicon.
It's always
Limicon.
Oh,
That was one.
looks like an ass.
Sometimes you have this like loop back on itself. So you've seen ones where it does like that.
That's probably where they got the name.
You see ones where it's just like that curve becomes a little bit like sketchier. So let me show you these on this. Plus B cosine.
Definitely not.
Definitely parts.
That goes A plus B sine theta. Okay, so
Put an N there.
as you add and subtract numbers to that B value,
Oh, well.
okay, we're gonna go cosine. It's less.
I'm deciding to put
Just turn your head.
Oh, really? So negative subtracts, and you just kind of get these little loopy things that happen. If I make B really large, like
What?
big butt.
Zoom out.
I'm not gonna lie.
Now it's the same size.
No, it's a moon. DreamWorks.
Where's little kid?
yeah. Okay, so that's the Limassol.
What happens as B approaches infinity?
I'd imagine that the curve becomes
Itself. Just
Yeah.
like a giant ass circle.
Oh.
Yep.
yeah. It approaches the 2 curves approach each other.
What is it?
Well, it's because the R value that you have, like you're adding a super large value for R, so that A becomes insignificant. And so basically it becomes R is equal to the other thing. That's why it's doing that. Okay. The last one are the circles and lemniscates. And I'm just going to kind of sketch these out a little bit. So r equals a cosine theta essentially is a circle with a diameter of a. You have r equals a sine of theta. What's that going to look like?
Opposite up.
It's just going to be up like that. And then you have these that are like little infinity symbols. And that comes from r squared is equal to a squared sine of like an n times a theta. So you can have cosine ones too. You don't have to memorize what these look like, but I want you to be aware of just kind of the general shapes you get and have a guide for that.